Hey, Katie.
Hey, Ben.
Shall we do some supervised learning today?
Well, so here's the thing, Ben, is that I have a little bit of supervised data, but I actually have a lot of unlabeled data, but I want to do supervised learning with it.
And we can't do that, right?
Turns out you kind of can.
Or can we?
Or can we?
You are listening to Linear Digressions. Okay, so what's the or can we?
Yeah, so this is kind of fun. This is a special case of what I would call ensembling, which is where you use different models together and you get something that's stronger than any one of those models by itself.
Mm-hmm.
And so
Ensemble.
yes, and ensembles are something that people use all the time right now. If you've ever heard of boosted decision trees or random forests, those are examples of ensembles. These are just what you do is you train several different models and you have them kind of vote in those examples on how a given example should be classified. This is something that's a little bit older. This use case is more from the 90s, but I think it's kind of cool. The idea here is we have a data set, some of which we have nice labeled training data, but we might have a lot more data which is not labeled. And so the question is there some way that we can use this unlabeled data to help us get a better supervised classifier? Does that make sense?
Kind of. Can you tell me more?
Yeah, so what you need here is you basically have two different algorithms that are structured differently. So you might have something like a decision tree, and I think in this example, the other thing was a decision graph.
Okay,
so it's
so
a
two
slightly different type
algorithms.
of algorithm. Yeah.
So two algorithms that are completely fundamentally different.
Yeah, they're structurally different. And then you train them on your sort of core little sample of labeled data. So they're learning the same data, but they're representing it in different ways. That's why it's important that you use two different types of algorithms.
Okay.
Is that then they learn sort of different representations of the data. They pick out different patterns in it. And then what you do is you take your unlabeled data and you take some of it, you send it to algorithm A. And you say, algorithm A, classify this. And some of it, and it'll come up with predictions for everything because that's how it does. And these predictions are probably, a lot of them might not be that great because it hasn't had the benefit of a really high statistics training set to fit on.
Mm-hmm.
But some of them, it's still going to be probably pretty confident about. It just looks really unambiguously for some example, like it's one class or the other. And so then you have algorithm A has classified these examples from your unlabeled data, which then it can send over to algorithm B, and it can use those as labeled training data for algorithm B. And then algorithm B can do the same thing, and it sends all of its good, predicted newly labeled data over to algorithm A as training data for that algorithm. And they go back and forth swapping.
So you've got, so let me just kind of rephrase this to make sure I understand this. So you've got some labeled data. That's your gold. That's the stuff let's say, is accurate, right? You train algorithm A and algorithm B, which are fundamentally different algorithms. And then you take the unlabeled data and you take a chunk of it, pass it to algorithm A, and use the results of that to analyze another chunk of unlabeled data. Okay, so we've got this passing back and forth thing. So what's the benefit of that? How does that get you more goodness in your data set? How does it get you more accuracy?
So let me give you maybe an example.
Okay.
Let's suppose that the problem that I have is whether Ben Jaffe is going to like a movie. And so maybe I'm Netflix and there's 50 movies that you've watched on Netflix, which is, enough to get started, but not a gigantically huge corpus of labeled training data where you've assigned them ratings and things like that.
Yeah, it's true. I don't watch all that many movies.
Sure.
Maybe 20 on Netflix.
Right. I mean, so Netflix uses a fundamentally different algorithm than this, but just for the sake of example.
Just for pretensies.
Yeah. But on the basis of these 50 movies, I might start to be able to say with fairly high confidence that there are some movies that I'm pretty sure that you're going to like and that I'm pretty sure that you're not going to like. I'm pretty sure that if you've seen 14 James Bond movies, that the 15th James Bond movie you're also interested in watching.
Mm-hmm.
And at the same in the same way, if you've never watched a children's movie, I can probably guess that like a children's movie is not something that you're very interested in seeing. And there might be some like borderline cases, like, oh, maybe there was you watched Pulp Fiction but no other Quentin Tarantino movies, and so I'm not 100% sure whether,
Or
a given Quentin Tarantino movie you're going to like it. Those are going to be the more borderline cases, but there are going to be a lot of movies that I can say with pretty high confidence yes or no. So imagine that we have this one algorithm that, let's say, based on the genre of the movie, is for some movies it's able to like classify with pretty high confidence whether you're going to like them or not.
mm-hmm.
Now let's suppose you have another algorithm, and instead of being based on genres, it's based on something like traits of the characters who are in the movies, maybe. I don't know. Like, let's say you really seem to love movies that have like strong female leads, which good for you because you're a good 21st century feminist, like like all the best men that I know. And so that's going to go through and it's going to learn a different set of rules for what movies you like and you don't like. And so it's going to come up with, at the end of the day, it's still training itself on the same data, but it's just finding different sets of patterns in it. So I don't know. Maybe James Bond was not a great example to use for the first one because it's not necessarily known for strong female leads, but you get the idea.
Yeah, I get the idea. And I also am kind of understanding a little bit more intuitively what you mean by two algorithms that are like structurally different, right? Maybe they could even be technically different.
Yeah. And in fact, I think in the case that that this paper was written about, they were actually different algorithms. It wasn't just you were using one algorithm but like trained slightly differently.
Right.
Because the goal is that it's learning the same set of data, but it has a different way of representing it. And so that would be, sort of the analog in this case would be we're going to learn the same movies, but just a different way of representing those movies. And so then algorithm B is going to have basically a different set of strengths and weaknesses from algorithm A. And so where algorithm A might be a little bit confused about whether you're going to like, let's say, Kill Bill, because it's Quentin Tarantino and it doesn't really know what you think of Quentin Tarantino movies, algorithm B is going to say, oh yeah, Kill Bill, that's right up Ben's alley because he likes strong female leads. And so I'm going to say with very high confidence that this is a movie that he's interested in watching.
Mm-hmm.
And
okay.
so those strengths and weaknesses, then each of them has sort of like a bigger data set that is accrued of labeled data, but they're not going to be overlapping exactly because they've learned their labels in different ways. And then they can swap the labeled training data that they're very confident on, and they can use that to kind of bootstrap themselves for the more marginal cases.
That makes a lot more sense to me. So basically you're taking the data points that each of the algorithms is fairly confident on, and you're actually using those data points to train the other algorithms on this unlabeled data, which is being labeled in, let's say, confidently by algorithm A or algorithm B or whatever.
Yeah, I would say that you've got it. So this is a special case of, like I said, something called ensembling, which is where we use not just one algorithm, but we use many altogether. And they don't always have to be necessarily structurally different. In this case, that was important to sort of get the back and forth kind of swapping thing to be working properly. But sort of the state-of-the-art algorithms that do best in kind of traditional supervised classification things. So if you're running something like you're trying to compete on Kaggle and it's just a supervised classification problem, probably the algorithm that is going to serve you best is a random forest. And a random forest is just a whole bunch of decision trees. And each decision tree has been trained on a different sort of subset of rows and of columns of the data. So they're learning different examples, and they're also learning different features for those examples. And each one of those trees is not going to be a very good predictor, but the goal is that altogether they're a much more powerful predictor than any one, super deep, complicated decision tree.
This feels kind of magical. Like it feels kind of amazing and magical to say that we can have a small amount of labeled data, train our algorithm, and then take unlabeled data and not only identify what we think it is, but actually use it to further train our algorithm. It feels like we're getting something out of nothing, which it feels like it violates like thermodynamics or conservation of momentum or something like that. But when you go through the examples, it makes a little bit more sense. Like fundamentally, if you're trying to solve a really difficult problem, you might put a number of people in a room, and then different people will have different strengths and weaknesses, and everyone will put their best foot forward and contribute their strengths and defer to others when it comes to their weaknesses. This almost seems like that, but with algorithms.
Oh, I think that's totally what it is. Yeah. And so then what you need in order for this to work is you just need to have, you don't even have to have necessarily all of the algorithms getting it right. You just have to have more algorithms getting it right than are getting it wrong in any single way, right?
I see.
Yeah. So as long as that's true, then this is going to, in general, serve you pretty well. I see what you mean about it being kind of like something for nothing, but
it just feels intuitively that way. It's not actually that, but it just feels kind of like, huh?
No, yeah. I mean, I guess the way I would think about it is that, so setting up something like this back and forth ensembling sort of thing. So random forests feel like pretty magical to me.
Right.
But for something like this,
forest.
Yeah, using this unlabeled training data, it's a fair amount of work to set something like this up, right? Like this is not something that you can get out of the box out of scikit-learn. But so it's a lot of work, and you need to have a lot of high quality unlabeled data for it to work. So yeah, it's not trivially easy to sort of get something this cool, up and running. But yeah, I see what you mean. Like it feels a little bit like you're getting away with something when you're able to train a supervised classifier on unlabeled data. But like I said, if you have the ingenuity, anything's possible, I guess.
Linear Digressions is a Creative Commons endeavor, which means you can share or use it any way you like. Just tell them we said hi. To find out more about this or any other episode of Linear Digressions, go to lineardigressions.com. And if you like this podcast, go ahead and leave us a review on iTunes so other people get to listen to this content too. You can always get in touch with either of us. Our emails are ben@lineardigressions.com and katie@lineardigressions.com in case you have comments or suggestions for future shows. You can tweet us at lindigressions. Thank you for joining us, and we'll see you next time.